All right. So I wanted to apply our newfound kinetic prowess to a couple of familiar situations. Last time we did the SN2 reaction. We're going to do, I'm sorry, an SN1 reaction. I'm going to do another SN1 reaction, only this one is with tertiary alcohol. And there's going to be this rapid pre-equilibrium. There's a forward rate and a reverse rate, but those forward and reverse rates don't matter because this rapid equilibrium is basically, we're going to assume that in the next step, what am I talking about here? In the next step, as soon as this alcohol gets consumed, it's going to be immediately replaced and arrive at a new equilibrium. So we're not going to worry about the influence of this step on the kinetics of the reaction. Then after this first step, you have a step to get the carbocation, which you can, which is an uphill high energy intermediate, which can go back to the protonated alcohol, and I guess water comes off. Alternatively, that primary or tertiary carbocation can interact with, say, iodide to give you this product. So to help our discussion along, we're going to call the alcohol R because, I don't know, because it is a reactant. And let's see what else. We've got the intermediate. I think we'll say, let's see how we did this. Oh, I didn't abbreviate things in my notes, so maybe I shouldn't bother with it now. Blurp. Okay, so you've got rapid pre-equilibrium. You've got a slower uphill to get the carbocation, and then you have a faster downhill to get your alkyl halide. So we can write a rate expression, but our goal is, since at no point do we know the concentration of the protonated alcohol, we're going to need a rate expression that probably includes the starting alcohol, probably includes the concentration of hydronium in our aqueous acid, and then probably includes I-. But we want to reflect the fact that this is a high energy intermediate and we're going to use the steady state approximation. Okay, so we would start out, you start out at the end. We'll call this product, whatever, this is the product. Start out at the end. The appearance of that product depends on rate constant 2 times the concentration of iodide times the concentration of your carbocation. All right, that's fairly straightforward. Those are words of death. Anytime somebody tells you something is fairly straightforward, you can be sure that it's not. So I apologize for that. All right, let's do the steady state approximation. Let's say that di, the concentration of intermediate with respect to time, equals 0. Now we're going to sum all of the terms that lead to that intermediate. The first is K1 times the concentration of our protonated alcohol. Let's see, is that right? The second is K minus 1 times the concentration of iodide times the, oh, sorry, I'm making stuff up here. This is the backwards reaction at this stage, so that would be carbocation and water, right? And then we are also going to subtract K2 times the concentration of the carbocation and I-. All right. Let's see. So for the steady state approximation, we get all the high energy intermediate on the same side of the equation, and we isolate that variable. So we won't do that algebra here, but we can say that the concentration of that carbocation at any given time is equal to K1 times the concentration of our protonated alcohol divided by K minus 1 times the concentration of water plus K2 times the concentration of iodide. All right, and so we could substitute all of this. I need another highlighting color. And I need a slightly bigger font. We could substitute all of this into the expression for the overall reaction rate. But we kind of have a problem in that our rate expression still includes a number that we're not sure what it is. Okay? And that is the concentration of the protonated alcohol. So now we're going to go back up to this reaction and try to reason through a few things. Is there any way we could use information we have to find out what that concentration for the protonated alcohol should be? Kim, you were nodding. Am I leading the witness? Because I wouldn't be talking about it unless there were an answer. What do you think?
Well, I mean, there's a couple things you could do, I suppose. You could set up another steady state approximation equation and substitute out the alcohol intermediate.
Okay.
Or you could know that in order for the alcohol to be protonated, it had to come from hydronium, and hydronium turned into water. So I suppose if you know how much water there is, but water's probably the solvent, so that's probably not the best rule to use. I'm not sure.
Okay. No, great thoughts. And in fact, water is going to show up in our expression. It has to, because it's an inhibitory product. If we have it there, it's going to go. We have the opportunity to go backwards. But you're right. If we make the assumption, you're right. We could do a steady state approximation. But if we assume that acid-base equilibria is fast, then this is not going to influence the rate of the reaction. We can assume at any point during the reaction that everything on both sides of this equation here is at equilibrium. So then all we need is to play around with the expression for equilibrium constant. Sure. No? Yes? Which is products divided by starting materials. Is that right? And if you'll let me, I'm going to turn this equilibrium constant into something that we might know a little bit better. Hold on. What does that start to look like? Especially if I move the water concentration over here. Yeah, starts to look like Ka. Yeah, and in fact, if we take this new sort of equilibrium constant and multiply it by the concentration of water, we've got Ka for the protonated alcohol. That is, how acidic is the protonated alcohol relative to water? And that's a value we can look up. We've got a table for that. Okay, but our goal is to get that protonated alcohol out of the expression for the rate so that we can have things in there that we know. So this then becomes pretty easy. Now the concentration of the protonated alcohol is simply concentration of starting alcohol times concentration of hydronium, pH, you can measure that, divided by Ka. All right? So now I'm going to put that number in place of my alcohol. So the concentration of carbocation at any given point equals K1 times concentration of alcohol, which presumably we can measure, times the concentration of hydronium. We can measure that by pH. And then on the bottom we have Ka times K minus 1 times H2O plus K2 times iodide concentration. You with me so far? Do you see what we did? So if you assume that that first step is an equilibrium step, then it's trivial to know at any given time what the concentration of that protonated alcohol is. All you need to know is what is the equilibrium constant for acid-base exchange there. All you need to know is what is the Ka, and then you can calculate the concentration of the protonated alcohol. Yeah, Kim?
Is there a reason why we're not using like pre-equilibrium assumptions that the rate forward is equal to the rate reverse, and we just shove everything over to one side and make the protonated alcohol?
If we did that, you would exactly get this expression. I haven't done, remember equilibrium constant up here, zooming in, is forward rate divided by reverse rate. So if you did that, you would get the exact expression that we did.
Yeah.
I think.
Yeah, you get like, you would get the alcohol times hydronium divided by water. Is that the same thing as calling water the Ka?
Yeah, the only reason we go to Ka is that we bundle water with the equilibrium constant.
Right, because I guess you'd have the rate constants also on one side.
Yep.
Okay.
Yeah. Good. So with that in mind, we can now come back to the expression, the rate expression for our product, which was all the way up here, K2 times K1 times concentration of alcohol times concentration of hydronium times concentration of iodide divided by Ka times K minus 1 times concentration of water plus K2 times concentration of iodide. So that's an expression that makes sense. We expect the reaction to be first order in alcohol, first order in hydronium, and we expect a complicated relationship with the iodide concentration, and it sort of depends on how fast that iodide step is relative to the backward step for water, right? What is going to happen if, to our expression, for example, what if K minus 1 times water, either because of the rate constant or the amount of water present, is really low relative to K2 times the concentration of iodide? What if this term swamps out that one? What'll that do to the denominator? Right, if this term is really small, we can pretend that it's not there. Isn't that great? Chemistry's great. You make assumptions, you make approximations, and it makes things simpler. So yeah, if that second step is fast, and remember, we're talking about basically an equilibrium process that looks like this, where the second step, the K2 step, has a much lower barrier. So this is a reasonable assumption. You get rid of that by making this assumption. You lose the water term, and then you can actually cancel out both rate constant 2 and iodide concentration to give you K1 divided by Ka times the amount of hydronium present. Then it simplifies substantially. Okay, and again, this is what you expect for an SN2 reaction of the alcohol in water using HI as the acid, because losing the leaving group is the slow step. In SN1, we expect that nucleophilic attack in the second step isn't going to be the rate determining step and isn't going to factor in the rate. We've shown mathematically that that's the case. And we've also shown how you take two things you can measure, your starting alcohol and your amount of hydronium and the Ka, and then you account for the amount of protonated alcohol you have present. Okay, any sort of questions about that? Yeah.
So we often talk about SN1s being, they're called SN1 because it's unimolecular. Is that just like, they're just talking about, we know that the second step is the rate determining step, and if you just wrote that out, ignoring the fact that the protonated alcohol is an intermediate, then there's just one thing there?
Yeah, so calling something SN1, nucleophilic substitution, unimolecular, the only way that works, because everybody knows SN1 is a multi-step reaction, is to say in the rate determining step, only one thing's involved. Okay. Though you have to, in order to get there, we had to make, the part where we make the assumption about what the rate determining step is really here, where we compared those two and we lost the iodide. Yeah. So I don't know. This is probably too much and a lot of math. I enjoyed it at least because it answered a question that I've gotten a few times in organic chemistry about SN1. Well, how come the nucleophile doesn't matter? It clearly participates. And the answer is, if that second step rate is fast, it factors out of the equation, which is kind of cool. All right. I want to test your test. That's a sensitive word right now. I will get your exams graded and posted to Learning Suite and then send comments to you soon. I will try to do that today. I want to test your sort of kinetic intuition by showing you a reaction. This is a nucleophilic substitution at a nucleophilic acyl substitution of the ethanol group for the chloride in our acid chloride. And experimentally, it is known that pyridine needs to be present. After the reaction, you make the ester, and then you make pyridinium chloride, the conjugate acid of pyridinium. And this sort of makes sense because if you think about nucleophilic acyl substitution, you're going to need somewhere for that proton on the alcohol to go, and there it is. All right, so it makes sense that you would need pyridinium. The controversy is there are a couple of possible mechanisms. One is that pyridine is actually has a catalytic role in addition to its proton pulling off role. All right. So this would involve, for example, the following few steps. You would have, we're not really doing nucleophilic acyl substitution, so you shouldn't feel like you need to scramble down this mechanism. It's fine to just sort of watch and think. If you decide to watch and think, then I'll just copy and paste from my other notes and we can just keep going. Alternatively, if you want to limit me on the amount of things I can talk about, let me just keep drawing. All right, so tetrahedral intermediate, leaving group leaves. You get this sort of weird positively charged amide that can't be too happy, and the pyridinium group is a good leaving group. So then in your next step, the alcohol attacks. You get a tetrahedral intermediate again. And lastly, we kick off the pyridine as a leaving group. And then finally, we're going to use pyridine as a base to, oops, I like to use red arrows, can't forget to switch, to remove that proton, and that will get us to products. All right? Go ahead.
How exactly is pyridine acting as a catalyst in that way? I mean, I can understand why if it attaches to the alcohol, because the lone pairs are going to be much more reactive than alcohol's lone pair, probably.
Yeah, so
How is it speeding it up?
Well, as you maybe learned in 351, neutral alcohols are okay nucleophiles, but not particularly strong. Chloro's a good leaving group, but before I've had students struggle to understand how that alcohol can attack the acid chloride without being deprotonated first. And I mean, probably the reaction will proceed to some extent without the presence of that pyridine there. But by having pyridine attack first, you generate a more reactive intermediate that the alcohol can attack quicker with.
It basically makes that carbon even more
Electrophilic.
so that
Yep.
the alcohol's more incentivized to attack.
Yeah, so that's wherein it is a catalyst and it gets kicked off unused. In the next step, it's a reagent because it gets rid of the proton.
Right, okay.
Yeah, go ahead.
But why would pyridine be such a good leaving group? Like, why would it even kick off chloride?
It's permanently positively charged if it's attached to that carbon,
Okay.
right? Like once we make the new nitrogen carbon bond, I guess I got to switch colors. Once we make the new nitrogen carbon bond, you got a positive formal charge on that.
So if it's a better leaving group than the chloride was in the first place, and that's what causes the reaction to the chloride with alcohol, then why was it able to kick off the chloride?
That's right. I don't know. It's a good question, and what we're really coming down to is relative rates. One way of asking the question you're asking is, how fast is the forward? Where's my pointer? Why isn't it working? There we go. How fast is the forward reaction here? We'll call that K1 versus K minus 1, which is the pyridine getting kicked right back off. And I don't actually know what those results are. And you could presumably do some experiments to verify that. So thankfully we are not, I don't know, that's kind of hand wavy, I know, but is it?
No, I mean, yeah, it makes sense. Like, I guess it's all just equilibrium, so I'd just be surprised that that's actually a better pathway than just.
Yeah, I guess the empirical observation is that adding pyridine makes the reaction go faster.
Yeah.
So, but you're right, there is an alternative. And so this is what chemists do when you have an observation. The alternative is, like you said, Jared, why does pyridine attack in the first place if it's an even better leaving group than the chlorine? And you can compare pKa's of HCl versus pyridinium. Pyridinium should be a worse leaving group than chloro. But in any case, you can think of a sort of a mechanism that doesn't involve pyridine catalysis where the alcohol attacks first. There would be some forward and reverse rate there. The chloro gets kicked off. Kicked off, but not ticked off, because it's happy on its own, happy being stable, because molecules are neither happy nor sad, they just are, which is how you know we're more than molecules. And I'm sorry, that sounded kind of funny. Whatever. I know that there are molecular explanations for emotion, so there we go. So in this mechanism, pyridine is only involved at the end to remove a proton. And that, if you think about pKa's, the pKa, and we should look up the pyridinium pKa. I don't remember what it is. I think it's around 7. Whereas the pKa of a protonated oxygen is going to be in the -2 area. So this is essentially irreversible, and one thing you should always remember is that proton transfer, by virtue of the fact that protons are small, is fast. Okay? So those are the two scenarios you've got. Can you think of it? Go ahead, Kim.
Sorry, this is probably just like not important, but I'm just curious. I feel like I remember learning in 352 that the pyridine decrypts alcohol first before the chlorine leaves. Do we know what order that happens in?
So you're proposing a third alternative mechanism
Well, I don't know.
where pyridine deprotonates the alcohol first,
And
then the alkoxide attacks.
No. Sorry. It doesn't change the mechanism at all. It's just that pyridine deprotonates.
Oh,
the
I'm sorry.
alcohol,
You're proposing that at this stage, pyridine does the deprotonating.
And then the chloro leaves. Yeah.
Okay. All right. I think that's a reasonable alternative.
That's not any different.
But if pyridine is only involved in proton transfer, that step is going to be fast, and my guess is it's not rate limiting, so my guess is it doesn't appear in the rate law.
Right.
Okay, so let's look at these two. Let's look at these two these two scenarios. With the first one, what do you think the rate determining step is? And to do this, just think about stabilities of intermediates and products. Go ahead. Yeah, it's probably the first nucleophilic attack to get a tetrahedral intermediate. We call it the tetrahedral intermediate because it is an intermediate and it's tetrahedral, surprisingly. Negatively charged, high energy. But once you kick off the chloro, you've still got a fairly reactive molecule, so probably you're going down a little bit, and then you go up again to a tetrahedral intermediate. So probably you'd expect some or most of these 1, 2, 3 steps to be involved in the rate to be part of either before or the rate determining step, I guess. How about on the bottom? What do you figure the rate determining step is? Probably alcohol attack, right? Okay. So we've identified the possibility of sort of any of these steps being involved in either possibly, I don't know how to say that. Any one of these might be the rate determining step or be before the rate determining step. So I think that's what I'm trying to say. Either RDS or before it. Okay, so can you devise an experiment that would distinguish between these two possibilities? What would you do? Go ahead, Austin.
So you do an experiment varying the alcohol concentration.
Okay.
Because if number 2 is the case, then the alcohol should play a role in the determining step.
Okay.
If number 1 is the case, then there is still potential to have the alcohol be the determining step, but
Okay.
there's less of a chance. You need the same 50
All right. So if you vary the rate of the alcohol here, you might expect, especially if this is the rate determining step, you might expect a fairly simple linear dependence of the rate on the alcohol concentration. Up here, you're right, depending on which is the slow one, it might be more complicated. Okay? What else? What other possibilities? And this is what chemists do. They do multiple things when you're analyzing kinetics. Yeah? Okay, remove the pyridine and see what happens.
Just see how far we go.
Okay, remove the pyridine and see if you can trap intermediates. Okay, cool. What else? Yeah, Kim.
Can you do this in any, maybe you can't find it, can you do this in any bases where they wouldn't participate, like they wouldn't attack? So like, you get something that will only deprotonate but not include
A sterically hindered base.
Sure.
Yeah.
I guess that's what I mean.
Okay, that's an interesting choice. A sterically hindered base, and see how that changes the rate.
Would affect protonation, but
Sterically hindered rate? What the heck am I?
but if you remove the purity, then,
Instead of pyridine? Okay. Let me ask you a question to because there is another possibility here that's pretty important. Let me ask you another question. What molecules, assuming, let's just pretend that this last step, the K3 to K minus 3, K3, K minus 3, let's pretend that last step is the rate determining step. That's why we're using air quotes, because we're pretending. What molecules should show up in the rate law? The alcohol, what else? Intermediates, depending on the steady state approximation, we might be able to substitute those out for something else. So you got alcohol, what else? One principle you may not have picked up on that the book says is steps before the rate determining step can also appear in the rate law. If they're fast pre-equilibria, they generally don't. But if, there's ways around it like we just showed you. But if steps before the rate law can appear, steps before the rate determining step can appear in the rate law. So what other molecules might you expect to see? Pyridine? So rate should be proportional in some way to alcohol concentration, pyridine concentration, probably your acid chloride as well, right? It's a starting material. How about on the bottom? What should appear in the rate law? Just your acid chloride and your alcohol. So one really easy way to test between these two scenarios is to just vary the pyridine concentration and see what it does. You might observe no change. If you observe no change, maybe it's option 2. You might observe a linear dependence, or it might be more complicated, and then you could go in and tease out some of the kinetic details. Dang it, I wanted to do another problem, but we kind of have to move on. Maybe I'll just modify your Chapter 7 study guide to make you do that problem. Evil. All right. So we're going to spend the rest of I spent too much time on my tirade today. We're going to spend the rest of our time thinking about competing reaction mechanisms and considering multiple reaction coordinates simultaneously. And I love this because I tried to do this in 351 and my attempt frankly sucked, and this is a much better way to do it, the way your text does it. But I'm not going to attempt to draw these things myself because it is difficult. All right. So this is a lot of stuff, and we're just going to focus for now on this option. Okay, this is a potential energy surface. The y-axis just represents energy, potential energy. All right. The axis that's coming out at us, I guess maybe we can call it Dang, some of you are going to get mad at me. Okay, fine. We'll call that Z. We'll call this X. We'll call this Y. The X-axis represents distance between carbon and the leaving group. These are substitution reactions, okay? Carbon leaving group distance. So up here where X equals 0, now I got to change pointer colors again. Up here where X equals 0, the leaving group hasn't left at all, and down here it's left completely. On the y-axis, we have distance between nucleophile and carbon. Okay? So if we were to, just thinking about it mechanistically, if we were to try to go from 0 in X and go all the way here, that would mean the leaving group left all the way before the nucleophile started to come in. That would be an SN1 reaction, okay? And then this would be in the second step, the nucleophile attacking the carbocation. That pathway is traced out for us in energy, and you can see you have to sort of pretend that you're looking at this with the ability to move all the way around. Maybe in some future version of the text we'll be able to move this, but if you sort of flatten this edge and that edge out, you've got a typical SN2 energy diagram, just with two different reaction coordinates. Here is your high energy rate determining transition state. Here is the carbocationic intermediate. The leaving group is left. Now the nucleophile comes in the second step. You're seeing that? Recognizing that okay? All right. Alternatively, if we go on the y-axis first, the nucleophile comes in all the way before the leaving group has left. That's an associative mechanism, and it generally doesn't happen for carbon, in part because carbon's too small. But it can happen for other kinds of things, especially things that are bigger than carbon. In fact, there's some question with substitution reactions involving phosphoesters, whether you get a trigonal bipyramidal pentavalent intermediate or whether it's just a simple substitution reaction. But notice for carbon at least, this isn't an intermediate, this is a high energy point. This is a place we would never go because it's an energy maximum, not leading to any particular well. In contrast, if the leaving group leaves at the same rate that the nucleophile comes in, then you're going to travel along this diagonal, and here is the SN2 transition state. It's closer to the starting materials than to the products. We're assuming that starting materials are higher energy than products. So, but at this point, the nucleophile has come in about the same amount that the leaving group is left, and that's our SN2 reaction. All right? You okay with that so far? All right. We can imagine this reaction, we can simplify this diagram by thinking about the top-down view. So just put ourselves on above the potential energy surface. So now we're just going to focus on we don't know what the energy differences are at this point. We can't see them. We're staring down the z-axis. And we're not attempting to plot them, but we're showing you, in this case, just the SN2 trajectory. And the pathway in orange marks the pathway you would travel along this potential energy surface as nucleophile leaves to about the same extent. A nucleophile comes in to about the same extent as the leaving group leaves, and in the black dot marks the transition state. So that's a little simpler to see. It's like we're just looking down on this one from above. We're not attempting to plot the SN1 trajectory, though it would be this edge and then this edge. All right. Now a question you can ask, which starts to get at the more complicated issues that starting OChem students want to know, which is a reaction SN1 or SN2? And the answer is it ain't that simple, because what you're dealing with are competing reaction coordinates, competing trajectories along the same potential energy surface. So we're going to assume for all of what we're going to talk about that the starting material stability and the product stabilities remain the same. But we're going to change the structure of our alkyl group. Now it's ethyl instead of methyl. Ethyl cation is a little bit more stable than methyl cation because of hyperconjugation or abridging hydrogen, depending on how you want to look at it. So what that does is it takes this corner and it moves it down in energy. That also, to some extent, moves this transition state down in energy, because by the Hammond postulate, the transition state resembles the carbocation, right? And frankly, it probably moves this transition, the second transition state, down in energy too, though we don't care because that's the rate, that's not the rate determining step. And so you would expect that the rate for ethyl chloride undergoing an SN1 reaction is faster than for methyl. Now, you've still got a faster alternative, the SN1 trajectory. But now, if you look at what the structure of the alkyl halide does to the SN2 trajectory, now it's curved. It's not linear. In other words, the nucleophile and the electrophile are not leaving. I'm sorry, the nucleophile is not coming in at the same rate as the leaving group is leaving. It turns out that the trajectory of SN2 is pulled a little bit to the left along the y-axis. So what that means is that the leaving group can leave even more before the nucleophile leaves. And this is a fairly general observation. If you have two reaction coordinates and you take one corner and you pull it down in energy, it's going to pull the transition state toward that corner. And you can see that it's been pulled that way. It's easier to see if you look at the overhead view. Here's our starting materials. Here's our products. This is the carbocationic intermediate. In orange is the SN2 trajectory. This is what it used to be for the methyl. The transition state has stayed reasonably close. Well, it's moved along both reaction coordinates. It's moved to the left along the nucleophile coordinate, meaning the nucleophile hasn't come in quite as much yet. And then it's moved further down on the leaving group leaving coordinates. So this would be a transition state that's a little bit more left, a little bit tiny bit SN1 like versus just pure SN2 like. This is the reason we didn't tell it to you undergrads in sophomore organic, because it's complicated and we all want life to be simple. But this is sort of how it is. So based on what I've told you, if you continue to add substituents to make the carbocation more stable, this is the secondary carbocation, you get to the point where the relative rates of SN2 versus SN1 start to compete. In this case, the SN2 transition state increases in energy because of steric hindrance. The transition state for SN1 lowers in energy because it's carbocation-like, and this is a more stable carbocation than we had before. But again, notice what pulling down on this corner of our diagram does. It tends to pull the SN2 transition state toward that corner. Yeah?
So when we get all the way to the tertiary carbocation, in 351 we're taught that SN2 doesn't happen. It's an SN1 reaction. Is it not necessarily that SN2 doesn't happen, it's just it looks more SN1-like?
Well, I think...
I mean, I can see that transition is super high, so...
I think the the statement "it doesn't happen" is maybe an oversimplified version of reality, which is, by the time you get to the tertiary alkyl halide, the energy barrier for the SN2 pathway, I mean, that pathway exists, but the energy barrier to it is high enough, and the energy barrier to the carbocation is low enough that you, provided you have, I suppose, a limited amount of kinetic energy, you go over this. Now, if you really turned up the kinetic energy, maybe you could go over that hill. Chances are you make a bunch of other things available too, and so it might not be that great of an idea. But even if we're going to say that we don't go down this SN2 pathway, if we did, the transition state would still be more carbocation-like, and that's plotted here. By the time we've lowered the energy of this part of our surface so much that it has pulled the SN2 transition state to be even less of leaving group, even more leaving group leaves and even less of nucleophile comes in. And that makes sense. If you were going to pull off an SN2 reaction, it would have to be the leaving group sort of mostly leaves and then the nucleophile comes in. All right. So these are called, these kinds of plots are called Moore, O'Farrell, Jenks plots. I don't know who these various people were. You don't have to remember them, but they can be useful in rationalizing kinetics of reactions. So I guess next time we'll talk about the one last thing, an example of using these to understand reaction mechanisms. And then we'll move on to chapter 8. So have a good weekend. We'll pray that there's a peaceful transition of power in the United States. Pray that the votes get counted.